So ionic compounds, a little more information about ionic compounds, great multiple choice questions. Ionic compounds are generally soluble in water, and the solution can, therefore, when you put in all water too, the solution has electrolytes present and has the ability to conduct electricity. At the molten state is when we take a solid and we don't dissolve it in liquid, we actually melt it, is what we call the molten state. It also salts your ionic compounds, which are generally salts. In the solid state, they will not connect electricity, so you cannot pass electrical current through table salt. However, if you melted that table salt, it would connect electricity as well. We're going to focus now primarily the rest of the time on covalent compounds, a little bit of information on covalent compounds. Going back to ionic compounds, a little note there: to conduct electricity, charged particles, electrons, or your ions must be able to flow, and that's the key for being able to conduct electricity. Covalent compounds, there's a sharing of electrons between nonmetals now. So this we move on to the structure, commonly found in individuals and molecules. They can form a 3D lattice network, like your ionic compounds can, and we see that with diamonds. Covalent compounds are attractive forces between atoms and bonds, attractive forces between molecules, or intermolecular forces. So we're going to start to deal with this. We've talked about the covalent bond. We're going to talk about now one molecule bounds to another molecule. We now refer to it as intermolecular forces. We're going to get into discussing those intermolecular forces. Intermolecular forces between molecules are generally weak, so covalent compounds are generally found as liquid or at gaseous state at room temperature. They will possibly be found as solids, but they will have low melting points. In fact, if we have a solid covalent compound, generally you want to keep a lid on it. If you just put some in a beaker and let it sit there, just open, exposed to the open air, it would actually begin to melt. Covalent compounds are generally poor conductors of electricity because the ions are, there's no ions actually present here. So we're talking about a sharing of electrons, so no charges were created. Some information about covalent compounds. First of all, we have single bonds, double bonds, triple bonds. We'll get into their strength as well, length and strength. Make sure you know them. So again, where we say a single bond, I will now talk about covalent bond. I will not show dots for the bond. I'm going to show a bar showing a bar represents 2 electrons, just so you understand that. One shared by each of the actual elements. So a single bond, I have 2 hydrogens, both have 1 valence electron, both want to have 2, well, we share it, and we can both act as if we're helium, so we have 2 electrons. A double bond is now a sharing of 2 electrons, the sharing of 2 electrons, 2 electron pairs, or a total of 4 electrons. Pay attention to that. 2 electron pairs, or 4 electrons. So again, there are total 2 bonds formed here, and again, we form a double bond. The triple bond is a 3 shared pairs, or a total of 6 electrons are being shared here in this situation. Nitrogen is an example of it, and it forms a triple bond. Now, we realize here as we move down from a single to a double to a triple, we actually get closer and closer together, so the bond length decreases. But as the bond length decreases, they get closer and closer together, they also get stronger and stronger in that relationship. So as we go down at the very bottom there, we see the bond length in the angstroms. We see it as the bond length gets less and less and less. You go from a single to a double to a triple. Yet with bond energy, we see it actually increasing from 163 all the way up to 941. So as bond length decreases, energy increases. That's make sure you understand that. The relationship between the two, the number of bonds increases, the bond length decreases. They have an inverse relationship. Yes, as the number of bonds and bond energy are directly related. Now again, we talk about in class, why is it not used directly by plants? Well, nitrogen and N2 forms a triple bond like we just saw on the page before. For the triple bond, triple bonds are too hard for plants to break down. So that's why when you look at fertilizers and stuff, you'll see ammonium NH4, or you'll see nitrate NO3. So the nitrogen and those bonds are both in a single bond. It's easier for the plants to actually be able to break them down. Electronegativity. Electronegativity is the ability of an atom to actually attract shared pair of electrons. We're doing one more trend here. Electronegativity, again, the ability to attract a shared pair of electrons to each other. Elements with a higher electron affinity accepts electrons easily. ionization energy, doesn't want to lose them. Well, electronegativity also will be high. It's actually a cousin to both these. We see them all following the same trend. The general trend of electronegativity is the same. It increases going up and to the right. And electronegativity is a relative concept, can only be measured relative to other elements. Therefore, there are no units on it. And the highest is your fluorine in the upper right-hand corner. Your noble gases are left off this chart because they are happy, they are inert, they don't want to react with anything. So the highest is up and to the farthest right is fluorine. Fluorine, I say, is our smartest element, has a 4.0. So the element with the highest electronegativity is fluorine. The lowest you're going to have there is cesium and francium in the bottom left-hand corner.